environment, the blockchain environment, is non-fungible tokens, soul-bound tokens, and you can organize community around. And definitely communities need some way for secure messaging, and probably, yeah, it was the main topic of our research. So definitely what we wanted to achieve, we wanted like to build a prototype of a chat without any administrators. And probably that's the biggest problem right now. That's for like in all of like the biggest messengers and groups, there is some administrator or a group of administrators which can control everything. So currently you cannot receive identity like sovereignty because of these administrators. So definitely they can decide who can be added into the chat. They can decide how and why like people can be removed from these groups. So definitely policies for adding and removing and updating like these chats are centralized and subjective. So definitely if you have like no some strict rules of how exactly this chat can be managed, it means that's up to administrator's decision. And definitely it leads to users cannot control their identities. Users cannot like take their chat history. They cannot take relations with another chat participant. So definitely I cannot control my account in the particular group because of administrators. But we can resolve that by introducing like some deterministic rules of how chats can be managed. And so we can replace administrators with some like deterministic logic of how we can add or remove people from these chats. For example, yeah, as I said before, you can have like clear rules how people can be added into the chat. For example, yeah, and we showed that in our like proof of concept that you can organize a community around non-fungible token owners, and you can take identifiers of these people like from their ownership. So if I have some, I don't know, non-fungible token, definitely this connected to my public key, to my external owned account. I can prove the ownership of this account by the digital signature and then use that as an identifier or as an identity in my chat. In this case, you can define like deterministic way of how people can join this chat, definitely by proving NFT ownership. In this case, you don't need to have any administrator or like you don't need to have any authority, which is allowed to like invite users. And definitely people can be removed from the chat by like the simplest variant is it's like common decision. So you can recheck accesses internally and define if the particular member should leave the chat. Additionally, you can have like more complex logic. So if you have some particular rules for the chat, for example, you cannot use particular words or particular like messages. It also can be proven, but that's like another topic of research. And of course, if you're building a chat, you need like to build some privacy preserving options. So when we tried like to implement the solution, we also focused on privacy, like yeah, and cyber resilience. Uh, so yeah, we thought how yeah which options you can support in chats and defined like 5 main ones. The first one, with our approach, you can build a fully anonymous chat. So it means you can prove the eligibility to type messages or participate in this chat, but without like any traceability with your primary account. So all messages are verifiable, but that's not known who exactly their sender. Then you can organize the mode where like people are still anonymous, but at the same time you can trace different messages and aggregate them by one account. In this case, I don't reveal my identity, but anybody can verify that there is a list of messages sent by the same account. Next one, if it's needed, you can build like totally transparent solution where all accounts and messages are public. The next mode is confidential. Confidentiality and anonymity is like a bit different properties. You can additionally to untraceability to allow users to encrypt messages like only for group members. And the next one, if you have some anonymous solution, you need to care about like denial of service. So definitely people can spam with transactions, with messages, bots can spam with messages, and you need to prevent like these abilities. And we were inspired by rate limit and nullifiers and also used them for like some separate our chat mode. Okay, let's switch to general flow. So initially, yeah, for example, I have some particular non-fungible token or soul-bound token. So I have my external loan account. That's a key pair, which is needed to make transactions on some blockchain, let's say Ethereum or like I don't know, Polygon, etc. Then I need to create an additional key pair, and this additional key pair will be used for messaging. So I'm gonna sign all messages and I'm gonna be authorized through this additional key pair. Why do we need an additional key pair? Because if we're operating with existing, SEC 256 key one curve, that's not very ZK friendly. If we're gonna like prove some statements and be authorized through zero knowledge proofs, it's better to have like some more friendly or more like compatible cryptography. This is the reason why we decided to use jab keys. That's BN 128 friendly curve. So it will not, yeah, it will reduce amount of constraints dramatically in final statements. So initially what people need to do is like generate additional baby jab key pair, and this key pair will be used for nullifiers in the future and additionally for authorizing your rights to send messages. Then I wanted to be registered in kind of registration tree. What does it mean? I need to prove that I'm actually an owner of a particular, credential on chain, and proving this ownership will allow me to add a particular record in this registration tree. This registration tree can be separated from the specific blockchain, so it can be built on, chat server or something like that. But if you want to like have synchronized histories between like some blockchain and this registration tree, it's better like to use to build that in the form of smart contracts. How I can be registered? It's like the first point where I need to generate a zero knowledge proof. A zero knowledge proof for what? I'm gonna be connected to some contract ID. For example, this contract with as a source contract with NFTs. I wanna like prove an ownership of which. Next one, I'm gonna like put NFT identifier, just like a specific NFT I own. Then I need to define my public key or external owned account. They have like the same identifiers. Then I wanna provide a verifiable credential ID. That's a like commitment for all data I wanted to prove in the future. So you can see that verifiable credential consists of like this account ID, NFT ID, owner, like external own account, my public key. That's a key I mentioned before. This like a public key from the additional key pair I'm gonna use to be authorized in messaging. An additional timestamp. Timestamp allows you to define where exactly this claim was created. So if I'm creating the commitment for all this data, it means I can partially disclosure them. So I'm gonna prove that I can prove that I'm an owner of a specific NFT, but revealing, for example, my public key or like without revealing other information. But the goal right now is to create a commitment for all data I wanted to include in this commitment. Then we have several private signals. So like private data, that's a timestamp, so it's better like to hide that, and public key. So this public key from this additional key pair. And then we need like to verify the following statement. We need to verify that verifiable credential ID was generated properly. So I know all data I included. And you can see that I'm not revealing my public key in this manner. So that's a private signal. And additionally, I need to prove that timestamp is defined in verifiable credential is lower than some well-known timestamp. Because if you're gonna verify that on smart contracts, you can like extract this deterministic timestamp and yeah, prove that you are not creating the claim in the future. Then user can sign the transaction with his external owned account with the primary key pair, use it for the blockchain, and send that. Smart contract verifies all data, verifies the proof, and if everything went properly, I have a particular leaf in this registration tree. We decided like to organize this tree in the form of sparse Merkle tree only because of simplifying membership and non-membership proofs. So finally, I have all data committed in my verifiable credential ID. So then I can prove like any statements on top of that. So the next step is authentication. It means if you're gonna send some message or if you need like to do something with chat, you need like to prove that you are authorized to do something. And it's verified by the following statement. First of all, you need to generate the signature. The signature using like this second secret key from additional key pair. You need, for example, to sign a particular message. So I want to like to send hello. I need to sign this message and send that to my chat server. But additionally, I need to create the proof that I'm eligible to send this message. How is this formed? Yeah, first of all, I need to define contract ID. If I'm an owner of the specific NFT, I need to prove that. And probably, yeah, this part of the logic is missing, but there should be, oh no, it should be like verified on-chain. It can be verified on-chain. If your chat knows about contract ID, which is allowed to type messages, it can verify that openly. But I need to prove that the specific data, the specific contract ID is included into my verifiable credential. Then I'm like putting registration tree root as a public signal, additional message, because everybody needs to know which message was signed by my private key. And additionally, some like timestamp to define the date and time of this message. Then private signals is my verifiable credential that additionally includes this contract ID. And if I was registered properly, I can prove that the same data is included into my verifiable commitment, verifiable credential. Then I need to provide a Merkle pass, which proves my position in the tree, and additional signature. So signature can be provided also in private manner. And in this case, you are proving the signature correctness in the circuit. So circuit logic is you need to prove that you have an entry in the tree with particular data, with particular public key. Then you're proving the signature correctness. And additionally, some timestamp. That is, for example, your credential is not expired yet. And then you can prove, you can send the message together with the proof to the server, and server can verify, everything. And if you're eligible, if you're owning a specific NFT and your registration procedure was like performed correctly, this is the reason why I'm eligible like to type some messages. Yeah, and actually that's full flow. And we constructed a design which allows you to implement different modes without like changing the circuit logic. So you can define additional selector, and this selector allows you to identify data you want to provide relating to the mode of the chat you're gonna use. So yeah, you can define some public flags, and depending on these public flags and these like public signals, you can use the circuit in different modes. So the first mode, as I mentioned, this like total and traceable is probably very close how authentication like circuit works. Additionally, if you're gonna like trace everything, you're extending the circuit with additional nullifier. If you want to like have all like public identity, you need like to remove additional like constraints, and you also can define that using the selector, etc., etc. So you can implement different modes without changing the circuit itself. It means you can use only one generated trusted setup for like all functionality I mentioned. So flags don't change the circuit. Yeah, they a bit like yeah, they make the circuit more difficult from one perspective, but at the same time, you still can prove everything like within a couple of seconds. All right. So how fully anonymous mode work? So yeah, as I said before, all messages aren't connected to the specific sender. So if I don't know, if I send two or three like or more messages, they're not connected between each other. So they are untraceable. And in this case, my auth-sensitive works exactly how I define it in authentication circuit. Probably one additional thing, if you wanna like to have a general purpose tree, you can organize that. It means this tree can collect registration for different owners of like different collections, different non-fungible token collections. But additionally, you can have separate trees. And for separate trees, you can define which specific contract can be registered in this tree. And this like slightly affects on the logic of the circuit. Yeah, the next mode is linkable anonymous. Yeah, we are extending our authentication circuit to with additional data. We need like to put nullifier. Nullifier, that's our identifier, which cannot be like traced relating to your public key or your external owned account, but that's needed to aggregate all messages sent by a specific authority, a specific user. And that's like format very in a simple manner. We need like to hash our secret key, and definitely if you are using the same secret key, the nullifier will be the same. But like using one-way hash function, we cannot like receive initial secret key, and so this again is not connected to my public key and external owned account. So we need to additionally prove that as I said, some contract ID is connected with contract ID, like related to our registration tree. Then we need like to prove that the public key was derived properly, and additionally that the nullifier was calculated properly as well. And last two constraints, they are allowing us to bind the secret key like relating to the public key and relating to nullifier we use. Again, we can implement this logic only with additional, yeah, adding additional selector, which defines which data we want to like to provide. And the selector itself can uh, can detect which logic should be implemented. Yeah, publicly identified, we also slightly modify our circuit, so we need additionally to provide the public key, and we are like proving the verification of the signature relating to the public key defined. So yeah, and additional, we need to prove that the public key corresponds to the public key defined in my verifiable credential. Yeah, confidential messaging. Yeah, all modes I mentioned, they don't presume encrypting the data with public keys of counterparties or like Yeah, they don't assume like any encryption, but definitely we can extend this logic with encrypting these messages additionally. Yeah, initial idea was like to generating the primary key by the sender of message and like re-encrypting them to public keys of counterparties. But actually, we recently started research with broadcast encryption. Uh, and yeah, I will touch that later. I will touch, yeah, about our progress. Then rate limited, as I said before, you can have a problem where some bots can spam messages. And if you're working in some anonymous like environment, it means you cannot detect who exactly spammed these messages. And we decided to extend our solution with additional logic that allows you to introduce like rate limiting nullifiers. These nullifiers don't reveal an identity, but only in the case you're sending messages only like less than defined times. So for example, if the logic of your chat is users don't need to send like, I don't know, more than 3 messages per second, it means you're defining a second epoch. And when people are forming messages, they're like providing additional data. And this like additional data is very connected to the secret key. And if people are sending more than 3, in my example, transactions, messages per second, they are revealing the secret data that allows you to reconstruct a secret key. So if people like increases the limit, in this case, you can reconstruct the secret key and punish the user with like additional logic. How it works, we are extending our authentication circuit with additional like parameter y, and it's calculated how it's calculated as a hash value of our topic. This is, for example, identifier of our epoch, additional secret key, and yeah, hash value of the message plus secret key. In this case, if you have, yeah, for example, we have limited our chat by 1 message per topic or per epoch. It means if the user generates 2 different messages and signs them with this mode, they generate 2 different access because messages are different. At the same time, they generate different Ys, but you can see that the one like component of each Y is the same. And it allows us having like 2 X's and 2 Ys. It allows us to reconstruct initial secret. So yeah, this is quite. Yeah, we can compare that with how Shamir's secret sharing works. So when you're sending more and more messages, you're revealing like more useful information that allows you to reconstruct the polynomial mental coefficients. It works like, yeah, quite in a similar manner. So if the user increased like previously set limits, they reveal their secret key. And for example, if initial deposit was made with the secret key or some stake was provided, definitely this user can be punished. Yeah, we have implemented the solution, and yeah, that's like usually that's quite efficient. For example, registration requires a proof that can be generated like less than 1 second, like 0.35 seconds. For creating a proof for the largest like rate limited message, it takes 1.38 seconds. And in the case of failure, if you cannot prove an existence in the tree, so you will spend only like a bit more than 1 second. Uh, yeah, circuits aren't like very, yeah, right now we're using gross 16 proven, but yeah, in our case it's totally okay because we have like only one setup for all existing logic. So you shouldn't like rewrite different, so you shouldn't like rerun setups for different subprotocols. And yeah, we can have one-time setup for that. Proven key, yeah, for the largest model is quite big, probably. Yes, still, but yeah, it's still possible to download them. And it requires, so if you want to like build the chat on the blockchain, for example, on Polygon, it will take 0.0116 dollars per message. But definitely, I think the majority of cases will launch their own chat instances on servers. You need to have the blockchain only for synchronizing registrations and yeah, accounting the current owners of the specific non-fungible tokens. Yeah, one more like point that recently we defined that the majority of like top messengers on the market are implementing encryption in chats by creating like a lot of bidirectional encrypted channels. And definitely it leads to quadratic like increase in the amount of like on complexity encryption complexity. At the same time, we have IRT construction, symmetric ratcheting tree constructions that allows you to build some kind of broadcast encryption key between different users, but actually messengers that use this approach don't control the verifiability of this like asymmetric ratcheting tree. And our next experiment is to build a prover that which allows you to prove the existence of the right position in the tree and build the final broadcast like group tree properly. Uh, yeah, I think that's it. Thank you for attention and if